Hello. In today's video, we're going to be looking at Lecture 17, Learning Objective number 3. So we're going to be looking at our sizes of our atoms and our ions. So when we talk about an atomic size, we're talking about the radius of that atom. So there are two methods that are used to determine the atomic radius because atoms are very, very small, and depending on what they're bonding with, they might have different atomic radii. So there's what's called the non-bonding atomic radius, which is called the van der Waals radius, and it's half of the shortest distance separating two nuclei during a collision of atoms. So when two atoms collide of the same type, it's half of that distance between. This is not the most commonly used one, because it doesn't really give us very much information about bonding, and that's usually what we care about. So we won't really look at that anymore at all, but I just wanted you guys to be aware of that one. We are also going to look at, the one we are going to look at is bonding atomic radius, which is going to be half the internuclear distance when two atoms are bonded. And I said this is kind of like an average thing. So they average it out amongst many, many different substances. So if, for instance, we take two nuclei that are bonded together, we'll do the circles first. So two nuclei bonded together. This is the internuclear distance, d, and the bonding atomic radius is going to be half that distance, so that will equal to 1/2 of that d. And the reason we can't get any closer, the reason we can't get these nuclei any closer is because of electron-electron repulsions. So I already talked about in the last video how the trend is for our bonding. So I was giving you the bonding atomic radii trend, which is decreasing from left to right. And the reason that this occurs is because as we go from left to right in the periodic table, our Z effective, so Z effective is going to increase going from left to right. So as we go across our periodic table, as we go in this direction, our Z effective is going to go up. So what happens, the reason that our Z effective goes up is because we are getting more and more protons in our nucleus, but we're not getting any more core electrons. So our Z effective goes up from left to right because the atomic number is going up, our number of protons, but the number of core electrons is not going up. And we can see this if we look at something like, let's take, I don't know, sodium versus phosphorus. So sodium is 1s2, 2s2, 2p6, 3s1. So all of these are core. So it has a total of 10 core electrons. And remember, our core electrons are going to shield better than our valence electrons. Now, and in the case of sodium, we have 11 protons. Go look at something like phosphorus. Phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. So we have the same core electrons. We have not increased our core electrons. So we have 10 core. And then we do have more valence electrons, but our valence electrons don't shield as well as our core electrons. And in the case of phosphorus, we have 15 protons. So we've increased our number of protons, but we have not increased our number of core electrons. So as we go from left to right across the periodic table, our Z effective is going to go up. Because our Z effective goes up, we're going to pull electrons in more. Electrons are pulled in more by the nucleus as we go from left to right across the periodic table. And when we do that, it's going to cause us to have a smaller nucleus, right? As we pull electrons in, our nucleus is that electron, or our atomic size is based on our electron cloud. So as we pull that electron cloud in, our atomic radii gets smaller. And again, most of our space is based on the size of our electron cloud. So we would say our electron cloud determines the size of our atom. So because we're pulling that electron cloud in, this decreases the size of the atomic radii. So as we go across, our Z effective increases, but as we go across, our atomic radii decreases. So we would say that we increase going from right to left, or our atomic radius decreases as we go from left to right across the periodic table. Okay. As we go down our periodic table, we are going to also increase in size. And this has less to do with our electron affinity than it does just we have more electrons. So atomic radius increases as we go down a group. So atomic radius going from left to right decreases because of increase the effective. Going from top to bottom, it is going to increase mostly because our n value is increasing and our number of electrons are increasing. And with more electrons, you have more electron repulsion, so they're going to want to get as far away from each other as possible. Okay, let's real quick look at ionic size. So when we're looking at ionic size, we're going to be comparing it to the size of the neutral atom. So we're going to say we compare to the size of the parent atom. And we're going to have our ionic size change based on if we were adding or subtracting an electron. So a cation loses electrons, or has fewer electrons than the parent atom. Two things occur because of this. One, fewer electrons, fewer electron-electron repulsions. Additionally, since we have the same atomic number, but fewer electrons, our Z effective has increased. So we have fewer electrons causing repulsion between other electrons, and we're increasing our Z effective, so cations are going to be smaller than anions. Or sorry, are always smaller than the parent atom. Now we can look at anions. Anions, we form anions by adding electrons. So because we have more electrons, we have more electron repulsions and a decreased Z effective. So our anions are always going to be larger than our parent atom. Okay. One last thing I want to talk about in this video is the idea of an isoelectronic series. So our isoelectronic series is a series of ions which all have the same number of electrons. We can also have an atom in there. Actually, let's not include the atom. So it's called isoelectronic because it has the same electrons. So in an isoelectronic series, the ionic side is going to decrease with increasing nuclear charge. So for instance, we could take the following isoelectronic series, O2 minus, F minus, Na plus, Mg2 plus, and Al3 plus. So these all have the same number of electrons, which is 10. So they all have 10 electrons. All have 10 electrons. And because they all have 10 electrons, but they have different number of protons, we're actually increasing our number of protons as we go. So name some number of electrons, increasing protons. Our Z effective is going to increase as we go across. So because we're increasing our Z effective, this increases Z effective. And hopefully we realize that as we increase Z effective, we're going to decrease our ionic radius. So our ionic radius will go the opposite way as our Z effective. Okay, that is everything for this unit, or for this learning objective. See you guys later. Bye.